All right, let's begin today's discussion with an acute triangle. So we have three acute angles. We'll label them capital A, capital B, and capital C. And what we'll do is we'll label the sides that are opposite of each angle using the lowercase versions of the same letters. So across from angle A is side A, across from angle B is side B, and across from angle C is side C. Now this is not a right triangle, so we can't immediately apply the definitions of sine, cosine, and tangent to relate the angles and sides. What we can do, however, is drop an altitude. We'll call this h1. And by dropping that altitude, we found a right triangle on the left side and a right triangle on the right side, which means we can use the definitions of sine, cosine, and tangent to write relationships within the right triangles. So let's start. Let's say the sine of angle A is equal to opposite over hypotenuse. And then on this triangle, I can say the sine of angle B is equal to opposite over hypotenuse from angle B's perspective. I've done this so that I have an h1 variable in common, and then I can perhaps say we can solve each of these equations for h1. So we'll have B times sine of angle A is equal to h1, and A times sine of angle B is equal to h1. And since both this expression and that expression are equal to h1, we can set these equal to each other. So what we've accomplished now is we have a relationship among sides and angles that don't explicitly reference the altitude we've drawn. So by using clever geometry, now we have a relationship using sine that didn't have a right triangle to begin with. Now, for the sake of aesthetics, why don't we put the same letters on the same side? So I'll divide both sides by little a, and I'll divide both sides by little b, so I end up in this situation. It's a very nice expression. But we don't have to stop here. What we can do next is say, well, why don't we eliminate this altitude and consider a different one? If we consider an altitude that way, we'll call this h2. Now we have a right triangle that involves angle C, and we have a right triangle that involves angle B. So let us perform the same analysis. Let's say we'll write down an expression for the angle C using sine of angle C is equal to opposite over hypotenuse from angle C's perspective. So that'll be opposite over. Then we'll write down an expression using the sine of B. So that's going to be opposite over hypotenuse from angle B's perspective. Okay. Then what we're going to do is recognize that there's an h2 variable in common. We'll solve both equations for h2. And then we'll do the same thing we did last time where we say this expression is equal to h2. This expression is also equal to h2. We can set them equal to each other. Then, for the sake of aesthetics again, we'll put the same letters on the same side. So we'll divide both sides by little c. We'll divide both sides by little b. And we'll end up in this situation. Now the best part is we recognize sine of angle B over little b in both of these equations. And therefore, by the transitive property of equality, I can combine them to write down a single expression, that is, sine of capital A over little a is equal to the sine of capital B over little b, which is equal to the sine of capital C over little c. This set of equations is what we call the law of sines. So the beauty of this is now we can erase the altitude h2 and pretend that we never drew it. And we can look at this triangle and say, thanks to the law of sines, we have a relationship that ties the angles to their opposing sides, and we have an equation that relates the ratio of the sine of an angle over the length of its opposing side. All right, now we have the law of sines for an acute triangle. It makes sense to ask, can we do the same thing for an obtuse triangle? So if we think of an obtuse triangle, A, B, C, and we label the opposite sides little a, little b, and little c, we want to drop an altitude. So let's drop the altitude from vertex C down to the side AB, which requires us to extend side AB, and then we'll drop down the altitude like this. We'll call this H1. So from angle B's perspective, I can write the sine of angle B is equal to the opposite side over the hypotenuse in that right triangle. So the opposite side is H1, and the hypotenuse is little a. Now, when I go and I want to talk about the sine of angle A, the problem is the angle A is over here. But the angle that's in my right triangle is this angle, which we understand to be pi radians minus angle A. So perhaps I could write this as the sine of pi radians minus angle A, and that would be equal to opposite over hypotenuse in that triangle. The best part, of course, is we have a trig identity that says the sine of pi minus an angle is the same thing as the sine of the angle itself. So we're right back to the position we were before, where we can solve for H1 on both. Solve for H1. And then equate these expressions. And then combine for aesthetics. And we have our very familiar result. So now, let's continue our discussion and say, what if we erased this altitude, pretend like it never existed, and let's make another altitude, H2. And this time we're going to try to make a relationship between angle C and angle B. So we're going to say the sine of angle C is going to equal to opposite over hypotenuse from angle C's perspective, H2 over little b. And then we'll write the sine of angle B is equal to opposite over hypotenuse from angle B's perspective, H2 over little c. And then we'll set them equal to H2. And then since there are two expressions both equal to H2, we can set those expressions equal to each other. And then we can put the same letters on the same side, so we'll divide both sides by C, and we'll divide both sides by little b. And we have this, once again, a familiar result. Then finally, we use the transitive property of equality to say there's a sine angle B over little b in each of these equations, which means this, and this must all equal each other. So we say once again, the law of sines is the relationship sine of angle A divided by the side length A is equal to sine of the angle B divided by the length B, and then sine of the angle C divided by the side length C. And this is the law of sines. So we have this for acute triangles and obtuse triangles. Great, so we have the law of sines, but the question is, what can you do with the law of sines? We're going to solve some triangles, meaning if you give me some information about the side lengths and the angles, then I'm going to find the rest. So our first example, let's imagine that we're given angle A is 70 degrees, angle C is 80 degrees, and side length A is 10. So if we try to draw a triangle out of this, we'd find something like angle A, 70 degrees, and then angle C is 80 degrees, and we know the length of the side opposite of angle A, so we know the length of that side. What we don't know is anything else. This configuration of information, we say angle, angle, side, like this. So the first thing we notice is the three angles in a triangle have to add up to 180 degrees. We have two of the angles. So if we write A plus B plus C has to equal 180 degrees, then we can immediately solve for capital B by saying 180 degrees minus A minus C. Now using the numbers 70 degrees and 80 degrees right here, we'll find that angle B is 30 degrees. So we have that. Now we're missing two side lengths. This side length would be lowercase b, and this side length would be lowercase c. In order to find lowercase b, we notice that we have a pair of information, angle A and side length A, that forms this ratio. And now we have angle B, maybe we'll write that equality down and solve it. So sine of angle A over lowercase a is equal to sine of angle B over lowercase b. And the piece of information we want is lowercase b. So we'll multiply b across, then we'll multiply by the reciprocal of this to the other side. Lowercase b is equal to sine of capital B multiplied by lowercase a over sine of capital A. Now we can fill in those numbers by saying lowercase b then is sine of 30 degrees multiplied by lowercase a, which is 10, divided by sine of angle A, which is the sine of 70 degrees. Now we can plug that into a calculator and get an approximation that says 5.32. That is the approximate length of side B. Now, to get the final side C, we can recognize that we have angle C and we have this ratio, so we can find the side C by the same mechanism. We'll go sine of angle A over lowercase a is equal to sine of angle C over lowercase c, and then we'll multiply c to the other side, multiply the reciprocal of this to the other side, and say c is equal to sine of capital C times lowercase a over sine of capital A. If we plug this into a calculator, we will find sine of capital C is 80 degrees, lowercase a is 10, and then sine of capital A is 70 degrees. So, calculator says C is approximately 10.48. So now we have C is approximately 10.48, and we have the complete triangle, all of the information. Let's try a different setup. This time, let's imagine we're given angle A is 60 degrees, side length B is 8, and angle C is 75 degrees. So if we start drawing this, we'd say, well, we've got angle A, 60 degrees, and angle C, let's put right up here, this is going to be 75 degrees. Now we realize that side length B is the opposite of angle B, but angle B is down here, which means we've actually been given this side length. This configuration of information we say is angle, side, angle, like that. Okay. Well, once again, we have two angles out of the three, and we know that the three angles add up to 180 degrees, so we know that A plus B plus C has to equal 180 degrees, which means the missing B is going to be 180 degrees minus A minus C. So if I take those two numbers and put them there and there, I'll find that angle B is equal to 45 degrees, like so. So we have now angle B. We're missing the side length lowercase a, opposite of angle A, and we're missing the side length lowercase c, opposite of angle C. So, once again, we recognize that we have a pair of lowercase b and angle B, opposite of each other. That gives us this ratio. So we're going to use that ratio. First, we'll start with the left equality. So we'll say sine of angle A over lowercase a is sine of angle B over lowercase b. What are we trying to find? We're trying to find lowercase a. So why don't we solve for lowercase a? We'll multiply a to the other side, we'll multiply the reciprocal of this to the other side, and we'll end up with lowercase a is equal to sine of capital A times lowercase b over sine of capital B. If we substitute the numbers, angle A is 60 degrees, lowercase b is 8, and angle B is 45 degrees. Now we can plug this into a calculator and get an approximation. We have 9.80. This is going to be 9.80. Now we have this side. The last side, we'll use the same argument. We have these two pieces of information in that ratio. We would like lowercase c, so we'll use the right equality. We want side length c, so we'll solve, multiply c to the other side, multiply the reciprocal to the other side. C is equal to sine of capital C times b over sine of angle B. Now, we plug it in, sine of, the angle C is 75 degrees, lowercase b is 8. And capital B, we found that earlier, is 45 degrees. We plug that into a calculator and we get an approximation, 10.93. So there it is. Our final side is approximately 10.93. So, if you notice, the two cases we just solved, we had two angles and one side, but in different orders. But as soon as you have two angles in a triangle, you automatically know the third angle because they have to add up to 180 degrees. So really, you can consider the last two examples we did to be different cases of three angles and one side. We're going to end here because the next case I want to bring up is going to introduce us to the idea of the ambiguous case using the law of sines. So, tune in next time for the ambiguous case. Thanks for watching.